Hello again. In the last video I'd made, we looked at some of these current shunts that were in the meters that I had damaged. So one of the things I showed you was how this little shunt out of the KASUNTEST ZT102 compared against this very large shunt out of a Radio Shack meter. These were both made out of the same material and they had the exact same resistance. It's just a lot less material used in the KASUNTEST meter, and that causes it to have a much higher watt density. So the KASUNTEST was up here at about 12, and the Radio Shack was at about 2 watts per square inch. And the whole thing that started this was when I purchased this KASUNTEST meter for a review, and I noticed this 20 amp input, and then when I looked in the manual they talked about having a burden voltage at 200 millivolts with this meter at the 20 amps. So I've already showed you that that would be very difficult to achieve in a handheld meter. But I thought it'd be interesting to modify a handheld meter to actually use it at 20 amps. So this UT61E is a pretty good candidate. And if you watched my last video, you know I tested the shunt out of a UT61E, and this is the results. This is actually the very first shunt that I tested that had failed. You can see the watt density for this particular shunt is quite a bit higher than the previous ones. So I know that to actually modify this meter, one of the things we'll have to do is replace that shunt. So I've got a friend of mine who gave me a piece of sheet stock of manganese, and I've gone ahead and I've cut that. You can see I have two different widths. This is about 40 thousandths thick. And what I'm going to do is put this into our little test jig here, and then we can run a sweep on it and see how it compares against the original shunt. You can see I've gone ahead and set up our piece of manganese. Alright, so you can see I have my SEM DT9939 in place of my X-Tech. We're going to use this to record our temperature data. I have the same thermocouple off of the Fluke, and I've set the resistance roughly to what the UT61E would be, which would be 10 milliohms. What I'm going to do now is sweep the current again from 3 amps up to 100 amps. Keep in mind that the shunt out of the UT61E, which is this one here, was damaged during this test. The watt loading for this piece is quite a bit better than that original shunt. We'll just see how this behaves. You can see at 30 amps we're already putting out close to 100 degrees Celsius, and we're dissipating roughly 13 watts. So it got pretty crispy, but it did not burn in two. Had a little bit of contamination on there. It started to cook off. My plan is going to be to use this little wider piece here. This is actually what I've done my calculations for. And this will allow me to get the watt loading even lower than for this piece. The original UT61E shunt is the white, and then the red is our new shunt that we just ran. This is looking at the current, and we can see that the original shunt failed somewhere around 80 amps or so. So this is looking at the voltage drop across the two shunts. Again, the white is our original UT61E, and you can see up in this area here it drops slightly more voltage. But what's interesting is you can see the curve for the resistance of the two is basically identical. You can see right here is where the original shunt started to melt. Of course, the resistance started going up until it broke down. So I suspect that our new shunt that we're going to make is going to be a little bit more stable than this. But again, we're going to be operating somewhere down in this region here. We're not going to actually run a meter with 100 amps through this thing. I have a couple of different needle nose pliers that I use for forming metal like this. I have this set here that is very flat and wide, and I have another set that are rounded. You can see with this I can basically make all kinds of curves. So combined these work pretty good. This is the original shunt out of our UT61E, and here is the new one. Because this has a lot more surface area, to get the same resistance this has to be a longer piece. So the UT61E has one adjustment for the shunt. It's this VR5. You can see it's marked in parentheses 10 amps. So what we can do now is we'll hook this thing up to our power supply and we'll fine tune this adjustment to get this meter back in calibration. You can see I have my 2 meters tied in series and they're attached to our large power supply, and we're currently putting out about 275 milliamps. And you can see both meters are reading roughly the same value. So with roughly 4.1 amps applied, you can see the 2 meters are reasonably close. Again, this meter has this adaptive backlight, so as it's getting shadows, you can see it's turning on the backlight automatically. So you can see underneath the meter, I've added this small piece of Teflon, and I also made this small cover. This will go over the top of the shunt, and hopefully that'll protect the meter as the shunt begins to heat up. Again, I'm not planning on pushing this thing much over 20 amps. This is looking at current at the top of the graph. We are at 21 amps, and if we look at the temperature for the two, again, the white is the UT61E, and we can see it's at almost 67 degrees Celsius. Our new shunt is about 52 degrees Celsius. It's still quite hot. You can see I have a few different 5AG fuses. These are not all for multimeters. This particular one is made by Little Fuse. This is a FLU11A. You can see it's rated for 1000 volts AC or DC. And we can see on the side it's rated for 20 kiloamps. This is made by Seba. See, it's a DMI fuse, 10 amps, 1000 volts, 30 kiloamps. This is a fuse that's made specifically for Fluke. It's a Limitron. You can see it's rated for 15 amps. Breaking capacity on this is 100 kiloamps, but there is no DC rating for it. So this is for an older style Fluke meter. This would be something that you would use for like a motor control. You can see it's a CC rating. You might use this for like a motor start circuit. This is a LP-CC-15. You can see here time delay, 150 volt DC, 20 kiloamps. You can see it's made by Cooper Industries, Bussmann Division, St. Louis. So this particular fuse would not be good for a multimeter. You probably remember when I was blowing up all these fuses, I'd use this little test block. And you can see I've added 2 clips to allow me to install these larger fuses. What I'm going to do is clamp this into our jaw, and we'll run some sweeps on these fuses. So let me get that set up. This is looking at the data sheet for this little fuse device. Again, this is the FLU series. This particular part is rated for 11 amps. We can see they have a curve here for the break time. So for example, the 11 amp fuse with 100 amps being applied looks like it'll break in about 0.1 seconds. If we look at the data sheet for the Seba, we can see they have quite a bit more information. So this particular Seba fuse I have is rated for 10 amps, and we can see they have a power loss of 1.5 watts. But notice they don't show that with our little fuse device. What we're going to do is install these fuses, and we're going to sweep all these to 10 amps, and let's just see what we get for a power dissipation and a temperature rise. You can see I have the Little Fuse FLU11 installed. It's currently drawing about 2 amps. And I'm going to sweep this from 1 amp up to 10 amp in 1 amp increments. See, the resistance of this is about 14 milliohms. Next up I have the Seba DMI fuse. This one again is rated for 10 amps. You can see the resistance for this is a little bit higher. This is the Limitron / Fluke KTK15. Next up we have the Bussmann LP-CC15. Again, this is a time delay fuse for motor control. So this is looking at the voltage drop for the 4 fuses. This first fuse, the blue, is our CBA. In green we have the little fuse. The white is our Bussmann LP-CC15. The red is our lowest voltage drop, and that's the Fluke Limitron KTK15. Let's see, again, we ran the same current through all of them. Some of them had a lower resistance, so I couldn't actually achieve the lowest current setting. Just looking at the power dissipation, you can see the CBA is dissipating roughly 1.8 watts. And again, this is looking at resistance. Looks like the CBA is 0.0165 ohms approximately. You can see it's definitely drifting upwards as it's beginning to heat. And the next one down is the little fuse, and that is 0.0130 ohms. And you can see that's again drifted up to about 0.0140 ohms. Next we have the Bussmann fuse at 0.011 ohms. And then our Fluke fuse at 0.01 ohms. So the obvious thing is that the CBA is a 10 amp fuse. This little fuse is rated for 11 amps. And then this Fluke fuse along with this Bussmann are both rated for 15 amps. Again, what we'd like to do is get to 20 amps. This data sheet is from Schroeder Electronic Corporation. UL recognized for 1000 volts DC, high breaking capacity of 20 kiloamps. Meets the requirements of IEC 61730-2. Also meets IEC standard 6269-6 and UL 2579 is a VDE certification and a UL certification. We give a ambient air temperature of -50 to 125 degrees C. So if we look at the 20 amp version of this fuse and we apply again 100 amps through this, you can see the break time is about 0.6 or so seconds. So this fuse is a little slower than the smaller parts. You would expect that it's a little bit more mass. Again, this is looking at resistance. So here's our new fuse, and we can see that has a resistance of about 0.0085 or so ohms. And again, it's fairly stable over temperature. So I've changed where I've attached that thermocouple. It's now resting against one of the fuse holders. The reason I've moved that is I think that'll give us a better representation of what the circuit board's temperature is doing. So you can see we're currently putting out roughly 1 amp, and that's what our little UT61E is measuring. And this is again looking at the temperature with our SEM, and the Bryman is looking at the voltage drop across it. So currently at 1 amp we are dropping roughly 20 millivolts. See, the temperature of this is slowly cooling. You see that with a graph here. So what I'm going to do is sweep this from 1 amp up to 25 amps, and again I'll just hold it at 5 seconds. Let's just see how hot the circuit board inside the 61E gets. So we're at 10 amps and we just broke 200 millivolts. You can see the temperature is starting to rise now. We're at about 40 degrees Celsius. Looks like we're dissipating roughly 12 watts inside of the meter now. You can see the UT61E over ranges at roughly 22 amps. Our temperature didn't get too bad, about 63 degrees Celsius. Just looking inside the meter, you can see there's basically no discoloration to the shunt yet. Looks in very good condition. So you can see I've been allowing the meter to cool back down. I'm still outputting roughly 1 amp through the meter, and you can see the UT61E is still displaying 1 amp now. So it's basically gone back into spec. What I'll do next is just apply 10 amps through the meter, and you can watch it with the clock, and this will give you an idea how fast this meter will heat up. And you can see with 10 amps being applied, we're dropping roughly 200 millivolts. Again, this KASUNTEST KT6000 had shown in the manual at 20 amps the burden voltage was 200 millivolts. You can see at 10 amps we're just now meeting that 200 millivolts. Looks like our camera is running out of battery juice, so hold on. So the camera ended up being full. I had to download all the data off of it, put new batteries in. As you can see, quite a bit of time has passed. But it looks like the temperature is now stable, so about 78 degrees. Let's just zoom out. Yeah, so this is the temp. Here's where it was cooling. You can see it's relatively flat now, so about 78 degrees. And you can see our current's gone up to 10.087. Of course, again, we are closed looped on current, and we're actually putting through 10 amps right now. So a change of about 85 milliamps. Again, being up at 78 degrees or almost 80 degrees C, I'm not too surprised that this is going to have some drift. So for fun, let's just go ahead and we'll take this on up to 20 amps, and you can see how long it'll take us to get from 78 degrees up to 100. Again, this is looking in the KASUNTEST manual, and we can see that 20 amps for no more than 10 seconds. I'm saying that our little UT61E is outperforming this thing hands down right now. Let's see, we're currently up at 110 degrees C. You can see our temperature is starting to roll off a little bit. See, the air is about 350 milliamps now. I think we're going to shut her down 160 degrees C. I don't want to damage the circuit board, so I'll just idle it back down to we can actually hit about 500 milliamps with it. You can see this is all just because of the heat. Let's just see what it looks like on the inside. Shunt still looks real good. This Teflon is very hot right now, obviously, but no discoloration in the shunt. Looks like it handles that 20 amps just fine. So it looks like our little Teflon spacers are doing a pretty good job. You can see that having the meter open for just that little bit of time, that the temperatures come down quite a bit, and the two are now getting very close. We're still about 70 milliamps off, but much better than what we were. Well, I think that's going to be it for this video. I'd like to welcome all you new followers. Glad to have you on board. So again, I'm still planning on buying a higher end meter to evaluate. I was looking at the Gauss and Metrawatts. I had written them about a transient protection accessory that they used to sell, and they wrote me back and said that it was a mistake, that they had placed it in the manual and they were going to go ahead and correct the manuals for it. So I don't know. I keep looking, and I'm half tempted just to wait for Dave's meter to come out and we'll run that one for you. So again, the KT6000 marked as a 20 amp input. You can see what we've done to this UT61E to actually get it to read 20 amps. But again, because of the high temperatures, it does drift around a little bit. But you can see it definitely can handle the 20 amp input without any problems. But again, this has got machine connectors on it. I've added quite a bit of copper in that area. That's a custom made shunt. So this meter's had a lot of work done to it. Well, until the next meter, later.